All right, so today we're going to look at the derivation of the Black Scholes equation. It's a topic that has caused a lot of heartache and pain for almost every single student that I've worked with. And I think one of the reasons for this heartache and pain is that in general, when you look at the derivation of the Black Scholes formula, you see that there is a fairly strong emphasis on the derivation from what you'd call the partial differential equation point of view. Today, we're going to take a very simplistic, a very simplified point of view. And the objective of this point of view is to actually build an intuition for exactly what does the Black Scholes equation do and how does it relate to some of the concepts that we studied so far. All right. So let's start with some basic context. The first element in our context is that we're assuming that we have a price series. And as far as this price series is concerned, this price series represents the behavior of some financial security. Let's assume it's an equity. Let's also assume for the second that this is an equity that does not pay a dividend. Right? And we will go out and say that this series, the one that we've just go down, that we just highlighted here, is represented by something called S of t. So one of the first assumptions that we make is that this price series itself is actually distributed or follows what we call the log normal distribution, which means that if you have a distribution which is normal in nature, and let's say this distribution is given by some variable x, then a log normal distribution would be given by e raised to the power x. All right? Now, the second assumption that we make is that ln, the natural log of st, which is log normally distributed, is actually ln of ex, which is x, which is normally distributed. I know this is possibly boring context, it's possibly stuff that you've already done that you're comfortable with, or possibly stuff that you're not comfortable with. But we just want to make sure that there is no confusion with respect to the assumption that we've just made. And the assumption is that the underlying price series is log normally distributed. However, ln of st is normally distributed, right? Okay, so now if we make this assumption, then we are making a few more adjustments to our context. And the first change in that context is, normally when we work with a price series, with a return series, or even with the behavior of a financial security, we say that, we expect to get some expected return given by mu, and we call this expected return. And then we expect some standard deviation, and we call this stdev. So in this revised context of st, of ln st, we want to introduce a few more variables. One variable that we want to introduce is ln st over st minus 1. Right? And what is this? This is our return series. This is the series that, for all practical purposes, should actually be equivalent to P1 minus P0 over P0. Okay, and on a related note, when we go out and make the adjustment that we've gone out and made in step 3 here, and we apply this adjustment to step 4 here, we find out that our expected return is R, which is free rate, minus half sigma squared. And this is something which is proportionate to time. Now, why R minus half sigma squared? If you go back to the basics and the fundamental setting of the Black Scholes equation, you'd remember that a Black Scholes model or a Black Scholes world assumes from the beginning that you're operating in a risk neutral world, and in that risk neutral world all investors are happy earning the risk free rate. And because all investors are happy earning the risk-free rate, all assets earn the risk-free rate, right? So in this specific case, we're actually saying that in this distribution that we're working with, specified in step 3 and 4, the expected return is actually not mu or r, but r minus half sigma square, and it's proportionate to time. And then we're also making the assumption that the standard deviation in this specific case is also proportionate to time. And in that specific instance, it's actually sigma into under root t. So what we've now just done is we've set the context. We've said we have something that represents a price series, which represents the behavior of financial security. We denote this by S of t. Then we go out and say that we're interested in the function ln, or a natural log of S of t, and this is equivalent to x, which is normally distributed, whereas st is log normally distributed. We then go out and say that we're looking for an expected return and a standard deviation for this series, and this standard deviation in return is given by these two numbers or these two figures, and that, in the end, what we're really looking at is the return series that we want to work with, which would effectively give us some indication of how high the relative percentage jump is from 1 second to the next, right? This is context. We haven't gotten into the derivation of our equation. All we're trying to do right now is simply get comfortable with the underlying assumptions that we will use in our next step. So now that we've really set the context, what we're really looking at is the probability that st is greater than x, is greater than equal to x, right? And we denote this probability by n of d2. And how do we calculate n of d2? We calculate n of d2 by, remember, what is the distribution that we're looking at? We're looking at distribution of ln st, right? ln st is normally distributed. And if you're looking at a normal distribution would basically say, okay, this is d2, and I'm interested in the probability of what lies on this side, right? So the probability st is greater than x is given by n of d2, and n of d2 basically denotes this part of the distribution, which lies effectively on the right hand side of d2. So we have a distribution. We know it's normally distributed. We know that we are given the mean and the standard deviation, and the mean is simply r minus half sigma square into t, and the standard deviation is simply sigma into under root t. So what can we do in this specific instance to actually estimate a standard normal variable, right? And the formula that we use, or the function that we use for calculating standard normal behavior is what? If you remember correctly, it's xi, which is the value that we're comparing, minus or less x bar, which is the expected number or the average, and these two divided by sigma, which is the standard deviation, right? So the framework is we need to calculate xi, we need to calculate x bar, and we need to calculate the standard deviation. Now, when you're looking at the probability that st is greater than equal to x, what exactly are you saying? You're saying that at this point in time, which is right now, at the point that we're standing at which the option is actually being evaluated, we have a price, and this price is given by s, right? And s effectively stands for s naught. We're also saying that there is a strike price in this specific case, and if the underlying hits that strike price, something interesting would happen. So if you assume that you're looking at a call option, if st is greater than x, you will get a payoff. If st is less than x, sorry, greater than equal to x, you get a payoff. If it's less than x, you get 0, no payoff, right? So for a call option, the probability that we're looking at is n of d2, which is the probability that st would be greater than x. And what would really summarize this question, this likelihood, is this calculation. Calculation which estimates the jump x over s, the value that we were looking at. Remember the framework. The framework is xi value minus x bar, the expectation, the average, divided by the standard deviation. So xi, our friend xi here, is actually ln x over s. And ln x over s is what? Ln x over s is the jump. I have an instrument which is trading, let's say, at 100. And this is my S0. I have a strike price that we've agreed at, let's say, 150. The jump that I'm looking at is ln 150 over 100, which is approximately 50%. And what I really want to compare is that, listen, if this is the value, how do I convert this to a standard normal variable? I convert this by taking this value, 50%, subtracting from it the expected return, dividing that by the standard deviation, and then calculating this number, and let's just call this number d, using this number d to find out what is the probability that st is actually greater than equal to x. Okay. So now if I extend what we've just done, remember the first step was setting the context. The second step here is working and identifying the framework that we're using for our calculation, and the framework that we're using for our calculation is the simple standard normal variate analysis, where we basically take a distribution which is not standard normal, and with a few minor adjustments such as subtracting x bar and division by standard deviation, convert to standard normal, and then use that to figure out what the relevant score should be. So our objective is, okay, we know what xi is. We already discussed what x bar is, which was given on our first slide. And we already know what standard deviation is. If we go out and replace xi with this, x bar with that, and standard deviation with the definition of standard deviation, what would we actually have? We would actually have ln x over s minus, remember, what's the expected return? The expected return is r minus half sigma square into 2 because it's proportionate time, and divided by sigma into under root t. Okay. So if I were to do this, you have to think about what is it that the standard normal variable calculates. When you do your standard normal variable calculation, you actually do something along these lines. You say, this is the value x, and I'm interested in the area under the curve before x, right? And we write this as saying the probability that st is less than equal to x. But the number that we want, sorry, is less than x. But the number that we want is not the probability that st is less than x. The number that we want is the probability that st is greater than equal to x. Correct? Which is not given by this segment, but is given by a different segment, and that different segment actually lies on this side of the bar. Correct? So what I'm really interested in is not this side, but this part of the distribution. So how do I go from probability of st is less than x to probability that st is greater than x? Because we're working with a normal distribution, we're very lucky, there's a simple check, and that simple check is 1 minus PR probability of st less than x is equal to probability st greater than equal to x, right? So all I need to do is 1 minus, right? But then this is 1. Second piece that we know is that 1 minus, and let's just simply say 1 minus, I'm looking at a probability d. This is 1 minus PR of D as far as the normal distribution is concerned is the same as PR of minus D. Or we write 1 minus N of D is the same as N of minus D, right? So all we need to do is multiply our analysis by minus 1, the work that we've done in the previous step here, right? All we need to do is multiply this with minus 1 and we'll have minus D. So if you multiply this with minus 1, what do we get? Right, so if we multiply what we've done with minus 1, what do we get? You know, our definition was, remember, framework is xi minus x bar by sigma. Xi is the jump, which is at an x over s minus r minus half sigma square into t, expected return, divided by sigma into under root t, which is distribution. Let's multiply this, call this a. Let's multiply a with minus 1. What do we get? We get minus 1 into ln x over s. This minus into minus 1 will give us a plus r minus half sigma square into t by sigma under root t. Right? Now minus 1 ln x over s is actually ln s over x plus r minus half sigma square t into sigma under root t. Separate this out. And this is effectively our PR minus D2, which is the probability, let's bring it here, which is the probability that ST is greater than equal to X. Okay. Now this formulation of D2 is the same formulation that we see when we look at the value of a call option or we look at the value of a put option. For a call option, the formula is given by Sn of D1 minus the present value, let's call it PVF, of X, the strike price, and the probability that ST would be greater than X. Right? This Nd2 is simply the normally distributed value of D2, which effectively corresponds to this chunk here. And to summarize, effectively what we've done is that we went all the way back. To setting the context for a discussion, one. Then we went ahead and defined the tool that we were using, which was basically converting the assumptions and the content and the context that we had to a standard normal setting. And then from there, we basically got to a fairly close discussion, made one specific adjustment for the fact that the probability that we're looking for was not ST less than X, but ST greater than X. And we finished it by simply driving or getting to the result for the value of D2 that we need to use for the calculation of a call option. I hope you found this useful. This is Jawad Ahmed Fareed signing off for financetrainingcourse.com. Thank you very much for your time.